In this video, we are going to talk about how the inductor behaves in a simple resistance inductor circuit. So here we are, a simple circuit. In the last video, we talked about the action of an inductor. We said that if there is current flowing through an inductor, then a magnetic field will be built around the inductor. Immediately the current changes. For example, if it changes from 0 to a certain value or from a certain value to 0, then the inductor will provide a counter voltage to oppose the current that is changing it. In other words, it will say, no, I will not allow you to change. So the inductor is always happy with the value of current flowing through it so long as it is stable. So if it is 0, if the current flowing through it is 0, it will want it to remain 0. If it is a certain value like 3 amps, it will want it to remain 3 amps. It doesn't like current changing from value to value. Immediately it does so, it will try to resist it. How does it resist? We said that it resists by inducing a counter voltage. That's what we explained in the last video. And the amount of voltage is said that it wants to impede or it wants to stop what is causing that change. The direction of the induced voltage is explained by Lenz's law. You can go back and revise that. And the induced voltage is as a consequence of Faraday's law. The current is producing magnetic field around it. So if the current changes, then the magnetic field will also change. If magnetic field changes, flux through the coil has changed. And if there is flux changing with time, we expect an induced EMF. Alright, so this is how the inductor works. We are going to see how it works in a circuit, combined with a DC circuit. We have a voltage here that is supplying current to the whole circuit. We have a switch here. We are going to use it to control the current that flows through the circuit. And this is a resistor. So we are going to see how this whole thing works. In this video, we have a source of electromotive force. That is a cell. Yeah, that one is pushing a current through the whole circuit. Indeed, this is the positive terminal and this is the negative terminal. The negative terminal has the electrons. Electrons will have to flow in this direction. But conventional current, we take it that the positive charges will be flowing, even though we don't see positive charges actually flowing. But we take it that conventional current flows from the positive terminal to the negative terminal. This video gives us a very nice picture in that the positive terminal has a higher potential. What do we mean by higher potential? What it means is that current flow from higher potential to a lower potential. So this part of the diagram has been raised to tell you that currents are flowing from this direction and they will end up in the lower potential area of the battery or the cell. Now we have a resistor here and we have an inductor here. This inductor has some material in it. For particular purposes, some materials can be put in the inductor, but what is important here is the coil. That's very, very important. So we can ignore the material that is within the inductor. This is a switch. There's another switch here. We are going to see how we use them to explain the action of the inductance. Okay, so let's see. Okay, so we are now going to connect the whole circuit, the circuit to the inductor. And let's see the initial reaction when the inductor is connected. There we are. So immediately the switch is connected, the inductor offers a counter EMF or counter voltage that opposes the EMF being supplied by the battery. So we have here force that is driving current in this direction. There's a counter force by the given by the inductor. In that case, if we have this force to be maybe whatever 12 volts, then this one will also be 12 volts at the initial stage. So immediately we close this circuit, this one will offer equal resistance to the current that will be flowing. But it will not last. It will gradually give in to the force that this one is supplying. So let's see what happens. Gradually, it starts decreasing its voltage, and this one takes over and start driving current through the whole circuit. And as this one reduces, the current through this circuit now increases. The current keeps on growing until the inductor does not supply any more resistance to the flow of current. So as this one reduces its opposition, the cell now push current through the whole circuit, and the current increases gradually as the inductor reduces its opposition. So that's the same as what we are seeing here. The source of the electromotive force, immediately we close this switch, the inductor will have to give an equal opposition to the voltage here. Now, let's try to see how the voltage across the inductor varies. I have a simple graph here. We have time on the horizontal axis, and we have the voltage across the inductor on the vertical axis. The voltage across the inductor on the vertical axis. So immediately we close the switch, that's when we start counting time, or we start measuring time. Time is 0, immediately we close the switch. So immediately we close the switch, the inductor will offer an equal opposition to the EMF. That means the inductor, the value of this voltage that is in opposition to the EMF will be the same. So the initial value will be the same as the value of the electromotive force. Then gradually, the voltage that opposes the electromotive force will start falling. It will decay. So as it slowly decays, the electromotive rather takes over and start driving current through it. As the voltage across the inductor decreases, the current also grows. The current gradually grows to the maximum. Let's see what happens when suddenly open the key here. After a long time, when the current is steady and flowing at constant value, the inductance relaxes. It is happy with this state and doesn't want to oppose anything at all. It will act like a straight wire that is not offering any resistance to the current. So what happens if we suddenly open the switch? So immediately we open the keys. The inductor doesn't want the current to stop now. There is a steady current flowing through it. So inductor will not want the current to stop flowing now. It will say, hey, I don't like what you are doing. And it will want to push the current flowing. So all that the inductor is doing is that it is trying to resist changes. It is trying to resist any change in current flowing through it. If it was originally at 0, if the current through it was originally at 0, it will want to maintain the 0. If you change it, it will say no, but then it will give in later on. If you want to reduce the current flowing to 0, it will say no, let it keep on flowing. I don't like the changes. So the inductor tries to resist changes, not resist the current itself, but it resists the changes in current. So now initially the current was flowing, and now we are trying to break the circuit. We are trying to say the current shouldn't flow anymore, and the inductor will resist. Let's see how it resists. There you are. So it will offer EMF or great voltage to keep the current flowing. Initially, when it was trying to resist, the force was in this direction to stop the current flowing. Now it wants to keep the current flowing, so it will offer a voltage that tends to push the current flowing. Now, a path has been given to the current to flow to avoid any problem. But if this path were not given, then the inductor will force the current through this one and it will cause a spark. So that's one danger in using inductors. If you are not careful, it will cause a great spark that will destroy our circuit. So if we tend to open the switch so fast, then the inductor will force current through it. I mean, you try to open it and there's a small gap. It will force electrons to move across the gap, and that will cause some sparks. So this is how the inductor reacts when we try to stop the current flowing through it. Indeed, there are magnetic fields around it. It is trying to stop the magnetic field changing. So it will offer a voltage in a direction such that the current will keep on flowing. Of course, it cannot maintain this voltage forever. It will offer the initial voltage, then slowly it will give in. Then the higher potential, which is momentum, will now drop. So the initial force given will now be relaxed. Then the current will gradually reduce to 0 again. So if we were to plot this side to be the current, then we can talk about the current flowing through the circuit at any time. So if this side were the current flowing through the resistor or the inductor, indeed, the current through the resistor will be the same current through the inductor at any given moment. So if the current, we have this axis to be the current, then initially the current will start from 0 and gradually grow exponentially. So this is a brief description of how the inductor behaves in a circuit containing the inductor itself and then a resistor. Let me also mention that the whole idea follows Kirchhoff's law. So the voltage across the resistor added to the voltage across the inductor at any moment should sum up to the electromotive force being supplied. So initially, at the initial moment, when the inductor offers the greatest opposition to this one, the voltage across the resistor will be 0. Then gradually, as it relaxes its opposition, it will lose the voltage and gradually shift it to the resistor. Alright, so we end our discussion on the RL circuit here.